Hello, learners. Greetings of the day. I welcome you all to the course on Introduction to Wireless Sensor Networks with the course code ECH403B-T. Wireless sensor networks are networks of small, low power devices that are used to collect and transmit data wirelessly. These devices, called sensor nodes, are equipped with sensors, processors, and wireless communication capabilities and are capable of measuring various types of data such as temperature, pressure, and motion. Wireless sensor networks are designed to be deployed in a wide range of environments such as industrial, agricultural, and environmental monitoring, as well as in healthcare, transportation, and security applications. Learning about WSNs is important for several reasons. WSNs are a rapidly growing field with a wide range of applications in various industries. As the Internet of Things continues to expand, the demand for WSNs is expected to increase, providing many opportunities for professionals with WSN expertise. WSNs involve a unique set of challenges such as limited power, limited computational resources, and limited communication capabilities, which require specialized knowledge and skills to overcome. WSNs require a multidisciplinary approach that combines knowledge of wireless communications, embedded systems, computer networks, and sensor technology, making it a challenging and interesting field of study. Understanding the design, deployment, and operation of WSNs is essential for the development of new technologies such as IoT, that is, Internet of Things, and for the efficient management of large scale sensor deployments. As WSNs are used in a variety of fields such as healthcare, agriculture, and transportation, understanding the technology can help in creating new and more efficient solutions in these fields. Overall, learning about WSNs can provide a solid framework for a career in IoT, embedded systems, and other related fields, and can help in developing new and efficient solutions in various fields. So, let us continue and learn about the WSNs and let's see the contents. So, we have wireless sensor networks introduction, and we have in the contents the WSN applications. So WSN applications, challenges for wireless sensor networks, the enabling technologies for wireless sensor networks. We'll see the single node architecture, the hardware requirements, and how the energy consumption in sensor nodes takes place. We'll see the network architectures. We'll discuss the network scenarios. What are the different scenarios in which a particular wireless sensor works? We'll see the communication system that is required, that is a transceiver. A transmitter and a receiver collectively is known as a transceiver. Then we'll see also the optimization goals and figures of merit for wireless sensor networks. So as you can see here, this is the basic architecture of a wireless sensor network, wherein which says wireless sensor networks are networks of small, low-cost sensor nodes that are equipped with one or more sensors, a microcontroller, and a wireless communication module. These nodes work together to collect and transmit data about the environment, such as temperature, humidity, light, motion, vibrations, and many others. WSNs can be used in a wide range of applications, including environmental monitoring, habitat monitoring, industrial automation, home automation, and healthcare. So a lot of wearable devices are coming into existence, and they can monitor your heart rate, your blood pressure, your oxygen levels, and all these information gets integrated into an app, and you can using an machine learning app or a device or a system that can collect this information and process it for you so that you can take necessary action about your health. So all these new technologies are coming because of the existence of wireless sensor networks, and the backbone to this wireless sensor networks is the uh, technologies that has existed in the past and has evolved so much uh, in the past. Okay, so this wireless sensor node you can see here, these are transmitting, these are various sensors. There's a source node. These basically nodes are acting as source nodes. They are measuring the pH level, the water level, the temperature sensors, all kinds of sensors are attached. And through these relay nodes, these acts as the relay nodes. These source nodes are sending data to the relay nodes, and it is again sent to the sync node or the destination node, which is the central gateway. And this, from this gateway you can also send this data through a relay node to the other node. So maybe this node is the sync node in case. So this source node can send data and can send through relay nodes through the gateway to the other relay node and send it back to the sync node, whichever one is the sync node in our case. So let's move ahead. This is a typical wireless sensor network scenario wherein you can see there is a deployment of nodes. Multiple nodes are deployed. There are sensor nodes as well as relay nodes, and all these are source nodes. And these source nodes collect data, sense data from the environment, send it to the gateway node, and this gateway node transmits this data to the mobile user or end user, remote user through a service called the internet. Okay, so this is typically a wireless sensor network scenario, how these wireless sensor networks work wirelessly. And the medium of communication is obviously radio propagation, radio waves. These radio waves are from the ISM band or the industrial scientific medical band, which is unlicensed frequency band. Okay, so let's see another example. This is a typical VANETs scenario. VANETs are vehicular ad hoc networks, vehicular ad hoc networks. In this typical scenario, you can see there is all these vehicles are attached to some sensors which are continuously sensing data like about the neighboring nodes, that is how many sensors are around a particular node, and it can be used for traffic management on streets, traffic management. So all these smart cities and the concept of smart cities and centralized traffic monitoring systems, all these are governed by these wireless sensor networks or networks that are formed through various uh, sensors attached to a vehicle. These sensor nodes track information about the neighboring nodes and also gives the how densely populated a particular region is. So based on the geographical region, it will sense the data about how many vehicles are there, or the like what is the density of traffic in a particular region, and this data is transmitted wirelessly through hopping. This neighboring node hopping is taking place in this particular scenario. See, this packet is transmitted here from here to here and from here to here on this node. So this is how transmission takes place through various nodes, and this is how VANETs work. This is one example. Considering this example where the formation of an autonomous mesh network is taking place, uh, this is various region-based routing protocols, and this source node here is sensing some data and it is transmitting to the sync node. The star one is the sync node, and this they are basically one hop neighbors. So it will, due to a technique called flooding, they are transmitting this data, and this data that is reached here to these nodes will be copied to these different nodes. All these nodes will send the copy to another node, and in this case you can see it is not getting connected to this node because both the nodes started to send the data at the same time, and they are not able to send the data to this node because node has failed, or there because of the congestion, or you can say the data packets that have collided in the way, and therefore it couldn't make a connection with this node, and so they are transmitting through this node. These nodes individual transfer it, and then this is how communication takes place in a failed node scenario. So in this case, this node fails. In the second case, so this is how it works. So this in this case, the node fails, and they are routing through these nodes. So this is how they work, wireless mesh network. So WSNs are characterized by their ability to collect and transmit data wirelessly, their small size and low power consumption, the and their ability to operate in remote and hard to reach locations. They typically consist of a large number of sensor nodes that are distributed over a wide area. WSNs are typically deployed in a distributed manner, with each sensor node operating independently and communicating with its neighboring nodes. The sensor nodes use a variety of low power communication protocols such as ZigBee, which is the IEEE 802.15.4 standard, and Z-Wave or Z-Wave to communicate with each other. There are other standards also like Wi-Fi, which is the IEEE 802.15.1, sorry, dot 11, 802.11 A oblique B oblique G oblique N. These are the standards for Wi-Fi. And there is Bluetooth, which is IEEE 802.15.1 standard. So all these standards are there. So what are the various applications for WSNs? So number one is the environmental monitoring. WSNs can be used to monitor various environmental factors such as temperature, humidity, air quality, and soil moisture. This information can be used to predict and prevent natural disasters such as wildfires, as well as to improve crop yields and water management in case of agriculture. Industrial automation. WSNs can be used to monitor and control industrial processes such as manufacturing and assembly lines. This can help to improve efficiency, reduce downtime, and increase productivity. In home automation, WSNs can be used to control and monitor various devices in a home, such as lights, appliances, and heating and cooling systems. This can help to improve energy efficiency and make the home comfortable to live in. In healthcare, WSNs can be used to monitor patients' vital signs such as heart rate, blood pressure, blood oxygen levels. This can help to detect and prevent any health issues such as heart attacks and strokes, and to improve patient outcomes. In military and defense, WSNs can be used to track military movement in the battlefield, surveillance, target tracking, and monitor of critical infrastructure. In agriculture, it can be used to monitor various environmental factors such as temperature, humidity, and soil moisture in agriculture fields. This can also be used to detect the soil content, like if a particular soil is good in nutrients, like if it has a good amount of nitrogen, so I can grow a particular crop there, and we can uh, have a better yield. Okay. In transportation, WSNs can be used in transportation applications such as traffic monitoring, fleet management. Just we have seen the example of VANETs. So this is one of the examples that we have seen for this particular case. Fleet management and monitoring of critical infrastructure. Disaster management. WSNs can be used to gather information during natural or man-made disasters such as earthquakes, floods, and chemical spills. This information can be used to predict and prevent disasters as well as to respond to them more effectively. What are the challenges for WSN? So let us see some of the challenges. WSNs have limited energy resources because they run on a typical AA size battery. So there is a AA size battery on which these sensor nodes work. So battery life is limited, and we have to increase the network lifetime. So for that we need to have low energy consumption. So as As long as there is low consumption, the longer is the life of the network or the node in the network. Okay, so sensor nodes in WSNs typically have limited energy resources such as batteries, which can quickly run out. This makes it important to design energy efficient protocols and algorithms for WSNs. Limited communication range. Sensor nodes in WSNs typically have limited communication range. That means you cannot transfer or transmit data to longer distances because of the range of the communication system, which can make it difficult to maintain connectivity also sometimes in between the nodes in the network. So sometimes connectivity also fails. And there is one property of wireless and sensor network that I wanted to share is that they have self-configuring capabilities. So they can self-configure themselves. Suppose a particular node is absent in a cluster or in its range, then it gets removed off, and new node that appears or a new network forms, suppose, and they can run automatically. And they have limited processing and storage capabilities. Sensor nodes in WSNs typically have limited processing and storage capabilities, which can make it difficult to perform complex computation and data storage tasks. So there is unlimited storage also. You cannot store all the data. So the cache node, the cache memory also needs to be cleared up. And you have a TTL, time to live, for the data on the cache to survive. Data on cache has to be updated. Okay, so because it is based on the TTL, time to live. So we have to predefine the time to live for a data to be available in the local cache, and the more is the TTL, the more is the data that is availability of the data on the cache memory. So new data will be updated only when you have the TTL as low as possible. So that's how this is a one of the constraints. So you need to have the cache memory, the TTL also, and you have to update the memory also, so that latest or updated data can be stored on the cache. So this is the another constraint. Then security. WSNs are vulnerable to a variety of security threats such as denial of service, attacks, and unauthorized access to sensor data. So all this data can also be breached, and security can be a major issue in WSNs. And the data that has been collected through these nodes can be compromised at some particular level. Then scalability. WSNs are often required to support large number of sensor nodes, which can make it difficult to design scalable protocols and algorithms. So if there are limited number of sensor nodes, it's easy to design a protocol for them. But if the number of or the population of the network is high, that means there is more number of nodes, like hundred, thousands, 10,000 nodes in a particular region, then the difficulty to design the protocol is increasing, and its complexity also increases for the computation and all, because the processing also increases and the computation obviously then increases. Then interference. When a large number of nodes are there, then probably they are configured to communicate on the same frequency bands, and probability is there that there is interference in the signals, and there is issues like hidden node problem, hidden node problem, and exposed node problem, which we'll discuss in later units. For the currently, we should have the names of these problems: hidden node and exposed node problems. And the seventh issue is the deployment and maintenance. Wireless sensor networks are often deployed in remote or hard to reach areas, which can make it difficult to deploy and maintain the network. Then the next issue is the quality of service. Wireless sensor network need to support various quality of service requirements, such as low latency. So the delay should be as low as possible, and the data should reach the coordinator or the sync node as soon as possible, and so that action can be taken. We cannot think of a situation where the nodes are sensing a data, say suppose at 10 a.m., and the data reaches after 10 hours to the sync node. So that is not possible for the real-time monitoring, and real-time monitoring is very important in, and that is why we are deploying wireless sensor networks, because it solves the issue of real-time monitoring, and that data should reach immediately through various sensor hoppings and all. Uh, it should reach the destination or the sync node as soon as possible. So there comes the reliability issue also. Reliability and quality of service are interlinked. A high reliability and high throughput, which can be challenging to achieve. So quality of service requirements, as you can see, there are a few factors like low latency, high reliability, and high throughput. Throughput means the uh, ratio of the number of data packets received over the number of data packets sent. So it should be as it should be as high as possible. So it should be 100%. So that means if I send 100 packets and if I receive 100 packets on the receiver side, then the efficiency of the system is 100%. Otherwise, it is a challenging task. So throughput should be as much as possible. In percentage, it should be 100%. However, it is in practicality, it is not achievable, but it should be at least 80% and above, so that you can have meaningful data. So let us see some enabling technologies for wireless sensor networks. So the technologies that have enabled the existence of wireless sensor networks include low power communication, which is possible through Zigbee and Z-Wave. Low power, that means they consume very less power, and this is how that is why their survival rate in the network is high. The longevity in the network is high. Then there is low power microprocessors, which rely on such as the MSP430 and Atmel AVR, which allows sensor nodes to perform computation and data processing tasks using minimal power. Low power radio transceivers. WSNs rely on low power radio transceivers such as CC2420 and CC1101, which allow sensor nodes to communicate with each other wirelessly using minimal power. So you see, every time we are using this word minimal power, minimal power, minimal power, so minimum power consumption is the main task. Energy consumption should be as low as possible, and energy efficiency should be high. For we can collectively call these three statements for energy efficiency. So as low as energy consumption is possible, then the system is good. Routing in MAC protocols, well, WSNs also rely on routing and medium access control MAC protocols, such as the routing protocol for low energy and lossy networks, that is the RPL, and the low power wireless personal area networks, that is the low PAN protocol, which allows sensor nodes to communicate with each other effectively and efficiently. So there are some sensors and actuators. Uh, WSNs are basically consisting of sensors on which rely on a variety of sensors and actuators such as temperature sensor, humidity sensors, light sensors, which allow sensor nodes to collect data about the environment. Data fusion and compression. WSNs rely on data fusion and compression techniques such as the Kalman filtering to reduce the amount of data transmitted and to improve the accuracy of the data. Security. WSNs rely on various security technologies such as encryption and secure key management to protect sensor data from unauthorized access and tampering. Then there is time synchronization. WSNs rely on time synchronization techniques such as GPS time synchronization to synchronize the clocks of different sensor nodes, which is important for correct data fusion, routing, and security. So this is a typical single node architecture of a sensor node. So this is a sensor node that comprises of various subunits. Number one is the memory, the communication device, the controller. There are some sensors and actuators, and a power supply that powers all the remaining four. So what does a controller do? A controller is used to process all the relevant data capable of executing arbitrary code. Memory, some memory to store programs and intermediate data. Usually different types of memory are used for programs and data. So I just told you that there is uh, RAM and ROM. So there is EEPROM, electrically erasable programmable read-only memory. That is the major memory device that controls all the sensing data. RAM is for processing all the data. processing. This is for storing data. This one is for saving data. Okay, all the sensed data has been stored. And sensors and actuators, the actual interface to the physical world, devices that can observe or control physical parameters. Then there is communication device. Turning nodes into a network requires a device for sending and receiving information over a wireless channel. Then we have power supply. As usually no tethered power supply is available. Some form of batteries are necessary to provide energy. Sometimes some form of recharging by obtaining energy from the environment is also available. Example, solar cell. So this power supply can be either double A size batteries, or we can have and other energy scavenging techniques like using solar cells for increasing the longevity in the network for the batteries to charge, increases the longevity of the nodes in the network. Okay, so this brings us to the single node architecture. Let us see how the energy consumption model in sensor nodes takes place. So there are three typical modes in which a sensor node works. One is the active mode, then there is the sleep mode and the idle mode. So what happens in these three modes? In active mode, the sensor node is fully operational and performing all the tasks. It is sensing data, receiving and sending data. Sensing, sending and receiving. All three modes are on. So that means it is consuming full power from the battery. All the parameters are being used, and so that means battery consumption is maximum in this case. So battery consumption is maximum, maximum in this case. Sleep mode. In sleep mode, the sensor node reduces its power consumption by shutting down non-essential components, such as if there is no transmission or reception going on, that means there is it can go to sleep mode. Okay, and it has sensed some data and it has gone into sleep mode. And whenever the data is required, the data can be fetched on request from the neighboring nodes, from the cache memory of the sense of the source node. So cache memory can also, in that case, energy consumption is minimum, or we can say not minimum but midway. The energy consumption is decreased to a certain extent and it is midway. Whereas in idle mode, the sensor node is not performing any task and is in a low power state, waiting for an event to occur. So, in just like when we are traveling on road and there is an ambulance behind us, it gives a beacon signal, and then you get an alert that okay, now ambulance is there, and we have to make way for that ambulance to move ahead of us. So, and that ways you stop your car, or you uh, move your car aside so that you can give way to the ambulance to move. So that beacon signal is required from the idle mode, from for the node in the idle mode to get into back into active mode. Okay, so beacon signal is there, and in this case battery consumption is the lowest. Battery consumption is the lowest. So the energy consumption of a sensor node in a wireless sensor network is a critical factor that determines the lifetime of the network. So the more battery is remaining, the residual battery is more, then the probability to survive in a network is, or the network lifetime increases. To maximize the lifetime of a sensor node, should be designed to consume as little energy as possible and to spend as much time as possible in sleep or idle mode. So the idea of designing a sensor or a routing protocol is to MAC protocol or a routing protocol, MAC plus routing, so as to keep the node in sleep mode or idle mode as much as possible so that it consumes less energy. Additionally, energy harvesting is another way to minimize the energy consumption in wireless sensor nodes. This way, energy can be collected from the environment. Example, solar, kinetic, thermal. There are piezoelectric transducers that can convert vibrations into electricity, and that can be used to charge the batteries or the onboard batteries to power the sensor node, reducing the dependencies on the batteries. So let's see the network scenarios in wireless sensor networks. So wireless sensor networks can be deployed in various topologies. So this one is called the star topology, in which there is a central hub and there are nodes deployed and connected to the central hub. So that is a star topology. Then a cluster based topology is where there is clusters, one cluster, second cluster, third cluster, in which each cluster has a cluster head, ch ch in this case, and ch in this case, cluster head, which is responsible for communication between the three. Okay, so this is a cluster based technology. Then there is hierarchical topology. In this scenario, sensor nodes are organized into a hierarchy, with each level of the hierarchy having different roles and responsibilities. This topology is more complex than the star and cluster based, but is more efficient in terms of energy consumption and scalability, as it reduces the number of messages that need to be transmitted to the base station. Okay, then there is mobile topology. In this scenario, sensor nodes are equipped with mobility capabilities such as wheels or legs and are able to move around the environment. This topology is more complex than the other but allows more flexible deployment and data collection, just like the example of manets. Okay, so this manets is mobile ad hoc networks. Mobile means they are in motion. Okay, some type of um, randomized motion is there, and mobile, and the nodes are mobile, and they may be moving in random direction or random uh, um, directions, and probability that they may get far from their clusters, and that this technology brings out the uh, uh, self-organizing capability of the WSNs. So this self-configuration and self-organizing probability is mostly seen in this mobile ad hoc networks. Okay. So then there is hybrid technology. In this scenario, sensor nodes are connected to multiple networks such as cellular and wireless, which allows for more flexibility and robustness in terms of data collection and communication. The network topology of a WSN will depend on the specific application, environment, and constraints of the development and of the deployment. Star topology is the most common and suitable for monitoring the environment, while hybrid topology is more suitable for monitoring a large area, and mobile topology is suitable for monitoring the dynamic environment. So dynamic environment means manets. So when we talk about the communication system of a wireless sensor network, that means that we are talking about the transceiver. Or transceiver means the transmitter and the receiver that we will be having on board in on the sensor node. So we have to have certain design considerations to be considered before we apply a transceiver on a sensor node. So it is a very crucial component of wireless sensor networks, as it is responsible for both transmitting and receiving data. Design consideration for the transceiver and wireless sensor nodes include power consumption, data rate, range, modulation, and there are other four also: frequency band, antenna, security, hardware size, and costs. So let us discuss power consumption. This is one of the most important considerations for the transceiver, as sensor nodes are typically powered by batteries and need to conserve energy to maximize the lifetime of the network. The transceiver should be designed to consume minimal power during both transmission and reception. Data rate. This is the rate at which the data is transmitted and received by the transceiver, and is typically measured in bits per second. The transceiver should be designed to support the data rate required by the application, while also taking into account the power consumption and the distance between the sensor nodes. Then comes the range. This is the maximum distance between sensor nodes that the transceiver can support. The transceiver should be designed to support the range required by the application, while also taking into account the data rate and power consumption. Then the modulation technique. This is the technique used to encode data on a carrier signal. The transceiver should be designed to support the modulation scheme required by the application, while also taking into consideration the data rate, range, and power consumption. So in the frequency band, this is the range of frequencies used by the transceiver and to transmit and receive data. Transceiver should be designed to operate in the frequency band required by the application, while also taking into account the regulations and interference from other devices. Then the antenna. The transceiver should be designed to work with an appropriate antenna, which should be chosen based on the range, frequency band, and the transmission power. The security. The transceiver should have been designed to protect against unauthorized access and should be include features like encryption, authentication, and secure key management. Hardware size and cost. The transceiver should be designed to fit into the physical constraints of the sensor node while also being cost effective. All of these design considerations must be carefully balanced to achieve the best performance and cost effectiveness for the wireless sensor network. The specific design considerations will depend on the specific application and environment of the wireless sensor network. So let us go on to the topic optimization goals and figures of merit. So we have seen the transceiver design considerations, we have seen the wireless sensor node, the single node architecture. We have seen how a wireless sensor network works, what are the applications, and now we'll be considering what are the optimization goals, like what are these um, services that needs to be checked in a wireless sensor network. So uh, it should be energy efficient. Number one, wireless sensor networks are designed for longevity. You cannot have, say, we are deploying nodes for say 7 days or 10 days or 1 month. It has to go longer duration. It should be deployed for at least a year to monitor a particular piece of land or a piece of geographic region, for that case of matter, to examine the habitat monitoring, for example, and for military purposes, for surveillance of warfare, warfield, and for aquatic life, like to monitor the habitat of the aquatic animals, and all sorts of things can be done for large buildings, also for surveillance of large buildings, for testing of vibrations against earthquakes and tremors. So energy efficiency should be as high as possible. Okay. So this is one of the most important optimization goals for WSNs, as sensor nodes are typically powered by batteries and need to conserve energy to maximize the lifetime of the network. Energy efficiency is usually measured in terms of energy consumed per bit of data transmitted, or the number of sensor nodes that can be supported by a given amount of energy. Typically transmission for 1 bit of energy, 1 bit of information, the battery requirement is nearly 35 nanojoules. Okay, it can be on slightly on the lower side or on or the higher side also, depending upon the case, because of the different where we have heterogeneous kinds of architectures now available these days, because we have Zigbee, we have Bluetooth, we have Wi-Fi, we have Z-Wave, we have hard sensors, HART. Okay, and there is another protocol called the ISA. So all these protocols are coming into existence because of the research is being going on these low power personal area networks, low power wireless personal area networks. So this kind of information is being, you know, technology is getting updated, and uh, this information can also change, but typically it is in the range of 35 nanojoules. Then the coverage. The most important part is that coverage should be as high as possible, because nodes should be deployed so that it should cover a particular geographic region. This is the area that is monitored by the WSN, and is typically measured in terms of percentage of the area that is covered by at least one sensor node. So then the third is connectivity. This is the ability of sensor nodes to communicate with each other and with the base station, and is typically measured in terms of the number of connected nodes or the probability of successful communication. Scalability. It should be scalable. The number of nodes should go up and down as per the requirements of the scenario. So this is the ability of a WSN to expand or shrink in size as needed, and is typically measured in terms of the number of sensor nodes that can be added or removed without affecting the performance of the network. So scalability is also one of the figures of merit. Then reliability. The data that is sensed should be reliably uh, transmitted to the sync node or the destination node, so that it can take some some corrective measures or some coordinating some kind of information. So the coordinator node has the responsibility to take necessary actions, to take the, to take up emergency measures. So reliability is most important. It is the ability of a WSN to continue to operate in the face of failures, and is typically measured in terms of probability that a message will successfully be delivered, or the number of sensor nodes that can fail without affecting the performance of the network. Latency, that means the delay should be as low as possible, that I have already discussed. This is the time it takes for a message to be delivered from one sensor node to another, and is typically measured in terms of the round trip time. Round trip time, or RTT, is basically sending the data to a particular node and receiving the acknowledgement. Okay, so that becomes the round trip. So if a data packet has been sent successfully to a neighboring node, it should return with acknowledgement and say that it has completely received the data packet. So otherwise it will keep on sending, or the bandwidth will be utilized again and again, and the network congestion may increase. So then there is throughput. This is the amount of data that can be transmitted in a given time period, and is typically measured in terms of bits per second or packets per second, PPS or BPS. Security. This is the ability of a WSN to protect against unauthorized access, and is typically measured in terms of the level of encryption used or the probability of successful attacks. So basically, these are the optimization goals, and figures of merit are interrelated and need to be balanced to achieve the best performance of the WSNs. The specific optimization goals and figures of merit will depend on the specific application of the WSN. Okay, so with this, we come to the end of the presentation, and this is basically the slides where I am sending you my email IDs. If you have any queries, you can share any query with me on these email IDs. And thank you for your patient listening. So we'll take up another unit in the next video, and we'll come back soon for our video lecture series. Thank you so much. Thank you for being patient.